Microscopic examination of cross-sections can tell us something of the artist's methods. On the video monitor linked to this instrument is a layer structure from an early Italian painting by Lorenzo Monaco. It is typical of egg tempera. This is a technique where the pigments are bound in egg yolk and are built up in separate layers. Lorenzo Monaco was one of the leading painters in Florence at the beginning of the 15th century. But this sample from the Virgin's robe contains a surprise. Looking at this today, one might assume that the artist chose the colour white for the Virgin because it was symbolic of purity. But scientific analysis has shown that he originally used a purplish red for the Virgin, a colour associated with regal or imperial power. Lorenzo Monaco used a transparent pigment, red lake, in a combination with ultramarine blue and white to create this drapery of heavenly purple. The red lake takes its colour from a dye derived from the lac insect. This colour we now know is fugitive. Over a period of time, it will fade through exposure to light. However, in some places, the final gilding applied over the purple has preserved the original colour.
This is the gold, the mordant gilding from the Virgin's robe, which protects the paint layer, and this is the glue or mordant, which is used to stick the gold onto the paint film. This is the mauve of the Virgin's robe, where it's being protected from light by the gold reflecting from the surface. And you can see here there are particles of ultramarine blue mixed with very bright red lake pigments in a matrix of lead white.
The optical microscope cannot always differentiate between similar colours when the particles are very fine. One example of this difficulty recently showed up in a painting by Rembrandt. In the past, it was assumed that Rembrandt used the expensive vermilion, or red mercuric sulfide, on the edge of the tablecloth, evoking his warm feelings towards the subject, his mistress, Hendrike Stoffels. But recent discoveries suggest that Rembrandt may have skillfully imitated vermilion with a cheaper combination of pigments. So how are you going to discover what this pigment is?
What I'm going to do is to take this cross-section, coat it with carbon, and perform an X-ray analysis on it using the large instrument next door.
We were to discover how the machine next door, the scanning electron microscope, was able to sort out this mixture of two pigments. In the Rembrandt sample, the machine had found a reddish-brown iron oxide and the more crimson-coloured red lake. The scanning electron microscope contains a gun which shoots electrons onto the sample. 3 detectors within the chamber at the base of the apparatus are tuned to pick up signals, either from the secondary electrons emitted when the beam strikes the sample, or from the backscattered electrons, the name for high-energy electrons rebounding off the sample, and thirdly, from X-rays emitted when the sample is being analysed. So the apparatus used by the National Gallery is able to produce 3 quite distinct analytical results. By interpreting the strength of signal from the secondary electrons, this machine is able to show a monochromatic image of the surface topography of a pigment. By their shape, these cabbage-like grains of pigment can be identified as emerald green, a brilliant colour first produced at the beginning of the 19th century. This sample has been taken from a large painting by the French artist Edouard Manet. The National Gallery's picture, one of several versions, was abandoned by the artist, and parts of the original canvas were cut away. What remains, however, shows why Manet was considered to be such a controversial artist during his lifetime. Painted in the late 1860s, Manet has depicted a newsworthy event, the execution of the Mexican emperor. At the time, this was a politically sensitive subject, and Manet's print of the execution was actually banned by the French censor. Having examined the surface topography of the emerald green, Dr. Bernstock now examines another part of the sample, combining 2 of the other analytical procedures offered by the scanning electron microscope. First of all, a backscattered electron image gives a clear monochromatic picture of the cross-section. Then, computer technology enables the operator to move a cursor around the screen, pinpointing an area as little as 5 microns across to be analyzed by EDX, that is, energy dispersive X-ray microanalysis. This method identifies the elements within the pinpointed area by recognizing the characteristic energy of the emitted X-rays. The computer translates the analysis into a visual form so that elements identified in the sample show up as a series of peaks on a graphic scale. In order to make comparisons, laboratory-prepared pigments are made up as a standard. Here, a 19th century recipe is being followed to create a replica of that brilliant but poisonous green found in the painting by Manet. So far, we have looked at the way in which scientists examine the fundamental colouring matter of art, the pigments. But the binder that glues those particles of dry colour to the support and protects them from the ill effects of the atmosphere is of great importance in the history of artist techniques. For instance, the medium of egg tempera, favoured by medieval artists, is basically a drawing technique, where the modelling is carried out by a sequence of fine lines, as can be seen in this panel painting by the Italian Renaissance artist Sandro Botticelli. However, the painter who grinds his pigments in poppy, walnut, linseed, or the viscous stand oil has a much longer time to manipulate the paints, either blending them wet into wet or creating subtle effects by overpainting with transparent glazes. The oil medium also permits the artist to build up textured surfaces. We are now looking at Rembrandt's Belshazzar's Feast, in a way that is not possible with egg tempera. Not only that, but the medium can modify the overall visual impact of the painting. In two paintings by Dirk Bouts, a 15th century northern artist, it is possible to see how different binders affect the colours. In his Virgin and Child, the linseed oil produces a depth of colour and great contrast between the lighter and darker tones. But in the same artist's Entombment of Christ, the head of the weeping woman looks matte and somewhat chalky by comparison. One of the reasons for this effect is that Bouts has mixed his colours not with oil, but with animal skin glue, a technique still used today for painting stage scenery. Drying oils react with pigments, and different kinds of change are sometimes noticeable. One is the increasing transparency of oil paint over a long period of time. And when the Dutch artist De Hoek made this interior, he began with a tiled floor and painted the figures over it. But since being made in the 17th century, the underpainting has started to show through. Another problem may be cracking and other aspects of incorrect technique that requires the attention of the museum conservator. So identification of the paint medium is just as important as the identification of individual pigments. Gallery scientist Jennifer Piltz demonstrates how this is done. In this tiny glass bottle is a solvent that contains the paint medium without its pigment. The pigment has been separated from the medium previously, and now all that is left is a colourless solution of organic components. These are then drawn up into a syringe and injected into a gas chromatograph. This machine separates the organic components from each other. It acts rather like a sieve, because the larger molecules take a longer time to emerge than the smaller ones. Once introduced into the machine through the injection port, the solution is pushed by an inert carrier gas round and round this extremely fine glass tube. As the molecules exit from the tube, they are burnt by a flame. The energy given off is detected, and this signal is converted into a trace on a chart recorder. Each type of medium has a characteristic fingerprint, so that different oils, egg tempera, or glue will all give different series of peaks, which can be interpreted to identify the medium. In the past, samples taken from paintings were consumed by the analytical process, either by heating or by chemical staining. But advances in technology means that today's samples can be analysed quickly and, most importantly, because the sample is not destroyed, for an infinite number of times in the future. We saw how the scanning electron microscope was able to investigate inorganic material in this way. Similar advantages are offered by this microscope, linked to an infrared unit. This enables Dr. Piltz to analyse organic material, such as paint binders, again without the destruction of the sample.
We can do this using infrared microscopy. The technique uses an infrared beam to excite the organic molecules, and the information collected is analysed by a computer.
Well, here you've got some very dark spots, which is pigment, and very rich red. So we try to avoid those areas and go for the paler bits around the edge here, where there's likely to be more medium.
The peaks in the spectrum correspond to varying energies that the organic components need to excite them, and from this we can interpret it to tell us what the medium was.
We have seen how the lake colour used by Lorenzo Monaco faded. In more recent times, the same colour was favoured by the 18th century portrait painter Sir Joshua Reynolds. The sitter, Lady Albemarle, today looks very pale, but we know that the lake colour was disappearing during Reynolds' own lifetime. Indeed, one of his male sitters, whose portrait had also lost its colour and had now a deathly complexion, wrote that Reynolds had made his paintings die before the man. Nothing can be done to stop the irreversible changes that begin once the painting leaves the studio or workshop. But control of the gallery environment can slow down that process. Monitoring changes in colour over the period of time is important in two ways. It is crucial for the development of more sophisticated environmental technology, such as lighting. It can also help the historian reconstruct the original impact of old master paintings. Researcher John Cupit explains how the gallery's colour measurement project will benefit scientists, curators and conservators.
Well, we illuminate the painting with light of 7 different colours and take 7 black and white digital images with the camera, which are then shipped across the laboratory into the back of the machine here. And we combine these 7 black and white images to make a single colour image in a standard colour representation. The images really have two uses. The first is that since the colours are measured exactly, the images are very good for the long-term study of colour change in paintings. In 20 years' time, we could take the same painting again and we'll be able to say exactly how the colours had shifted, which is something that isn't possible with conventional photography. The second use is that since the images are on a computer, you can manipulate them in a variety of ways. You can enhance details that perhaps aren't obvious to the naked eye.
Gallery scientist David Saunders is responsible for monitoring the gallery environment. This computer screen shows some of the results of data collected by sensors located in each gallery. Air temperature and humidity must be controlled to minimize atmospheric change around the paintings. And not only that, the daylight entering the gallery must be prevented from falling directly on the surface of the pictures. If it does, colours will fade, and other unwelcome changes in the condition of the painting may be accelerated. From here in the roof space of the gallery's new Sainsbury wing, the results of such scientific research are put into practice. In the galleries below, the art of the past prevails. But without science, our knowledge of how these artists worked, of what paints they used, and how best we should preserve their paintings would be dangerously meagre. Thanks to the sophisticated application of science, the future of these valuable works of art is assured.